Hi there, and welcome to another episode in the Geology 101 Physical Geology video series. I'm Geology Professor Shawn Willsey, and today in episode 17, we're going to take the knowledge we've gained in learning about the three different rock types and the processes that govern those rock types. And now we're going to start to sort of play detectives and figure out how these rocks, when they're intertwined together in more complex relationships, how we can figure out the chronology, the sequence of events that have played out that form the geologic riddle that's presented to us when we go out into nature. So this video series, of course, Geology 101, is modeled after the class I teach here at the college. It's the same curriculum. Everything's pretty much the same. And you can supplement what you might get with a field trip or a lab experience by looking at some of my other videos here, and I'll put a few relevant ones here in the video description. So let's just get right to it here. We're going to be looking at what are called relative dating principles, basically ways to figure out how old one rock is relative to another. And we do this with people all the time. We see maybe two individuals, and we use various points of data to determine who's older than who. Maybe it's gray hair, maybe it's wrinkles, maybe it's fashion. Could be a number of things, right? And luckily, with the rocks, it's a lot more simple and straightforward than trying to figure out ages of people, because humans can vary so much in their appearance. So getting right to it, we're going to basically look at how, especially the sedimentary rocks play into this. Some of the principles and rules we're going to use here apply to all rock types, but there's a few of them that are best suited for the sedimentary rocks. And so we're going to learn four basic principles, four rules, if you will, that is really going to help us determine the relative ages of rocks. And so you can look like a super hotshot smarty pants on your next little hike outside with your friends by using these rules or principles and being able to determine which rock is older than another. Now, we're not going to, in this video, get to how we know how old the rocks are definitively. That's what we call absolute ages. But we will spend another episode here coming up soon looking at how geologists can determine the specific ages of rocks. So again, this is relative dating, just basically putting rocks in order, looking at geologic events and putting them in order based on their relationship. So here's our first principle, our first rule. And almost, I think the names of these rules is more difficult and more confusing than actually applying them. So our first rule is original horizontality. Sedimentary rocks, are deposited in horizontal orientations or close to horizontal. And the idea here is that sediments tend to accumulate in depositional environments that are largely pretty horizontal. A lake bed out in the ocean, along a beach, maybe it's a slight slope. In a sand dune, it might be a little bit steeper, a riverbed. And the idea is that sediments will be deposited in more or less a horizontal orientation. So that when we see beds of rock that are not in that horizontal orientation, that tells us that that event took place after those rocks were deposited. Again, it's simple logic. You probably could have figured a lot of this stuff out yourself, but these principles are very important and very powerful as we apply them to geology. So any folding, tilting, or faulting of the rock has to occur after it was deposited. So here we have a little person here along the beach, and we can see these rocks are tilted. And if you look actually closely up here, you actually can see a little bit of a fold. So this is actually probably a very tight fold in the rock, and there's a little bit of an erosional chunk that's removed here. But the basic premise here would be if we have tilted rocks that are sedimentary, those rocks have to begin horizontal. So our two sequence of events here would be the rocks were deposited, mostly horizontal, and then later they were tilted, or in this case maybe folded, into this orientation. You can't use this with metamorphic rocks because metamorphic rocks can produce the folding or the tilting or the crazy layering you might see at the time of metamorphism. But sedimentary rocks, this is a principle that applies specifically to our sedimentary rocks. So there's principle number one, original horizontality. Principle number two is superposition. Basically, if you have an undeformed sequence of sedimentary rocks, the oldest rocks will be at the bottom and the youngest rocks will be at the top. So here's a nice photo I took down at Capitol Reef National Park. The red rocks at the bottom here are part of the Moenkopi Formation, a Triassic unit. Sitting above them are some of these gray and purple layers here. This is the Chinle Formation, which is also Triassic in age. And then sitting above them is the Wingate Sandstone. And so these rocks are getting younger as we go up. One layer is successively deposited on top of another to form this sort of relationship. Again, a very basic principle, but one that is quite powerful. Notice in the text here I have a bolded, yellowed term, undeformed sequence. So generally, it's a good place to start and assume that if you have a sequence of sedimentary rocks, the oldest is at the bottom and the youngest is at the top. But there are places where nature can really trick us, and entire sequences of rock can get actually not just rotated, but completely flipped over. It happens possibly more often than you think, and it's something to be aware of. And so this might be a little situation where you might run into this. So let's say we go over here to one location, and our budding geologist here checks out the rocks and sees that the sequence of these sedimentary rocks goes from conglomerate at the bottom to limestone in the middle to sandstone at the top. But maybe they hike over a few kilometers or miles away, go to some other location, and they see the inverse relationship with sandstone at the bottom, limestone, and then conglomerate on top. And let's assume that the layers here are the same, that they're very certain this sandstone is very distinctive. Maybe it's a green sandstone with certain fossils, and it's the same one we find over here. Well, then this person's got a little bit of a dilemma on their hands. They've got to figure out which one of these locations correctly displays these sedimentary units in their correct order from oldest at the bottom to youngest on top, because clearly something's awry here at one of these locations. And so you may have an instance like this where the rocks have actually been inverted. It doesn't happen that often, but it is something to be aware of. So there's principle number 2, superposition. Do you remember the first principle? Original horizontality. Okay, and these two principles apply best to sedimentary rocks, or I suppose volcanic rocks, rocks that are deposited at the surface, can sometimes follow this relationship a little bit, but you need to be careful once you go outside the sedimentary world. Our next principle applies to all rock types, and I think that's why it's maybe my favorite. It's maybe in some realms it's maybe the most useful, and this is called cross-cutting relationships. Again, it's another basic one that is very logical. Any feature that cuts across rocks, and the two features that are most common here would be dikes and faults, those features have to be younger than the rocks they cut. So here's a photo from Iceland. You can see this thin intrusion cutting up through the rock layers. This is this dike here. So we've got a sequence of rocks, more or less layered rocks that are close to horizontal, and then this near vertical dike. And so the interpretation we would then glean is that this dike has to be younger than the rocks that it cuts. Again, very simple principle, but one that's really powerful. If we look at it from a faulting perspective, here's some beds of sediment, and you can see where like this black layer is offset by, it looks like one, there's one right here, so 2, 3, at least 4 faults, 4 prominent faults that have offset the beds, and they kind of form this stair-step pattern here. So our principle, when we apply it to these rocks, would tell us that the faults have to be younger than the beds that they cut. Again, it's simple logic, right? You can't cut something until that something exists. I can't cut you a slice of birthday cake until someone has actually baked that cake and it actually exists, and then we can slice it and cut it. Same thing with faults and dikes with the principle of cross-cutting relationships. So pretty simple so far. Original horizontality, superposition, cross-cutting relationships. Okay. Oh, one more thing here on cross-cutting relationships. Here's a photo of me down in the Grand Canyon. Faults and dikes are the things you'll see quite often, but you can actually also apply cross-cutting relationships sometimes to contacts, erosional contacts. So here, just below my knee level, is the Vishnu schist, a metamorphic rock. You can see the foliation or the layering in this is near vertical, and then there's an abrupt contact. This is actually the great unconformity, an erosional contact, and then there's a bunch of sandstone where my hand is stacked above it, the Tapete sandstone. So this erosional contact cuts across the layers below, so therefore that erosional contact would have to be younger than the rocks below. So that there's another sort of application of the cross-cutting relationship principle. Okay, on to our fourth and final principle, inclusions. Any rock fragment that's inside another rock has to be older than the rock that it is within. So for example here, little set of keys for scale, looks like more like a granite or something here. And then we have this darker rock, this inclusion or xenolith inside the granite. And our principle of inclusions would tell us this has to be older than the rock that it's contained in. Excuse me. Or for in this example here, we have some particles in a bedded sedimentary unit, and all these particles here above the rock hammer would have to be older than the actual rock that they're contained in. Again, it's simple logic. So inclusions is our final one here, our last principle of inclusions. I like to sometimes call this the chocolate chip principle. And I sometimes think of these inclusions as chocolate chips that are inside the cookie. So the idea is here is what comes first, the chocolate chips or the cookie? And you need the chocolate chips first in order to actually make the cookie, because the cookie is formed around the rest of that chocolate chip, or around the chocolate chip. So principle of inclusions. Pretty simple, right? Feeling pretty good? So we're going to do some quiz questions here and see how well you learn these four basic principles. So if you need some time to digest those, you can go ahead and pause the video. Otherwise, we'll jump right to a couple of fun little quiz questions and see if you can apply this knowledge in a variety of situations. So here we have a diagram, little person here with their rock hammer, a bed of sandstone, a bed of limestone, very simple, and these are cut by an intrusion of basalt. And so the question here is you have to figure out the younger and older part of the equation and then which principle you're using. So go ahead and pause the video if you need a little bit more time. Okay, so let's fill in the blanks here. The basalt is blank than the limestone due to the principle of blank. Well, the basalt is a dike that is cutting across the limestone. So therefore, using the principle of cross-cutting relationships, I know that the basalt is younger because the limestone needs to already exist before this intrusion of basalt can cut across it, which would be at a later time. So the correct answer there was D. Hopefully you did pretty good. These start out pretty simple, but I'll slowly take the training wheels off and make them a little bit trickier and a little bit more complicated. Let's go to the next one. So what I have here is a photo of a rock, and G represents this particle within the rock. X represents this particle within the rock, and the letter P designates the entire rock. So your job here is to pick out which one of these 6 statements is true. So go ahead and pause the video if you need to. Okay, let's go ahead and apply our knowledge here. So this is an example of where we're especially going to use the principle of inclusions. We have G and X are inclusions inside rock P. So X is the youngest. Is that a true statement? No, X is a particle inside of the rock, so it can't be the youngest. Same thing with G, so those two are out. Then we get to statement C. X and G are older than P. Well, they're both particles or inclusions inside of P, so that is our true statement right there. So the answer there was C. And please don't answer number F. That would just hurt my feelings. And maybe that's your grade for the day. Oh, okay. Let's go to the next one here. So here we have a sequence of sedimentary rocks, these kind of colors in the background. And then we have 3 different dikes that cut these rocks. Dike A, Dike B, and Dike C. Your job is to figure out which of those 3 dikes is the youngest. So go ahead and pause the video if you need some time to figure that out. Okay, so this is a fun example of using different relationships. And we're again going to use cross-cutting relationships, but remember we can only really compare 2 specific geologic features to each other using cross-cutting relationships. So we might observe, for example, that dike A cuts across dike B, therefore it has to be younger than dike B. We might also go over here and look at dike B and dike C and see that dike B cuts across dike C, therefore dike B would be younger than C. Now dike A and dike C don't cut each other. They don't share space, at least in this diagram. But because dike B is a feature that's common to both, we actually can infer the full sequence, the full history here, and answer this question. So if dike let's see, if dike B cuts dike C, that would make dike B younger than C, but then A cuts B, making dike A younger than B. So therefore, dike A is the youngest feature. Are you still with me? Are you getting sleepy? All right, let's keep going. Let's do another one here. I think I have one or two more after this one. So which rock unit is older? We have a simple contact here, granite below, sandstone above. Go ahead and look at your options there, figure out which one is older, pause the video if you need to, and then we'll answer this question. Okay, so let's see how you did here. We have a lot of different options here. This is the question that I usually get all my students on. This is where they think they've got it. It's pretty simple. They're in cruise control. And then this question kind of jumps up and bites them in the butt. So we have granite, we have sandstone. Where I get a lot of people, and maybe I got you, and that's okay. Mistakes are meant to be made, and that's how we learn, is the granite sits below the sandstone. So a lot of people like B because they're like, oh, granite's on the bottom, sandstone's on top, superposition, moving on. But remember that superposition only applies to sedimentary rocks. Granites are magma bodies that form underground. They are igneous rocks. They play by very different rules. They do not form at the surface. They can be brought to the surface later. And because of that, you cannot infer any direct relative ages using granite in a sequence like this. So what is the right answer, you might say? Well, the correct answer actually was E. You can't tell me for sure that the granite is older than the sandstone because there is a story and another version where the granite might be younger than the sandstone. So what I need to do, I really want to look at this contact closely and see if there's any other evidence that can help me figure out this age relationship. So let me show you that in a little bit of detail. So there is a story where the granite is older, okay, but not because of superposition. So there may have been, if you start at the top here, older rock, we don't know what that rock was, doesn't even matter. Magma intruded into that rock. That magma then cooled and crystallized to form granite. Okay, that would be our step number one. Step number two would be that granite, that older rock, was eroded away. The granite even was eroded and weathered a little bit. You can see the rain coming down and little chunks of granite sitting on the surface there in this very irregular erosional surface. So the granite gets exposed, whoops, and then the sandstone gets deposited on top of that. So that's one story. Now, if this story is the true story, what I would want to see along that contact is maybe some evidence of erosion, maybe some inclusions of granite inside the sandstone, right at the base of the sandstone. Are there chunks of granite right there? Because if there are, I can then use the principle of inclusions to tell me that the granite is older than the sandstone. So there's one story. That's one viable story based on that very simple photo I showed you, that very simple relationship, granite and sandstone in contact with each other. But there's another story. There's another story shown over here on the right where the sandstone is older. So in this story, we could start with a sandstone deposited at the surface, and then later magma intrudes into that sandstone, probably introduces a little bit of alteration along the margin. Maybe there's a little bit of contact metamorphism here. That magma ultimately cools and crystallizes into granite. And then maybe just for fun, I kind of did some big erosion here, kind of cut down into it so we could actually see that contact right there between the granite and the sandstone. So this is also a viable story. If this is the true story, when I go back to this photo here, what I might look for, I'm going to look closely at that sandstone right at the bottom. Does it show any evidence of contact metamorphism? Does it look like the heat from the magma altered that sandstone in any way? And that would be some of the evidence you would want to look for. So that one might have got you. The correct answer was E. More information is needed. I need more evidence. I need more data from this contact in order to tell definitively which rock unit is older. So tricky one there, right? Just when you thought it was so easy, it gets a little bit more complicated. But be careful with those principles, right? Be careful with applying superposition to any stack of rocks. You need to know what the rock types are. Okay, sedimentary rocks, you're fine. If it's other types of rocks, igneous and metamorphic, they play by different rules, and superposition may not be valid in that case. Okay, let's do, I think this is it. I think this is my last one. No, I've got one more beyond this, so we'll do two more if you're not already just going crazy. So here we have, this is from Joshua Tree, a few different features. We have granite, this kind of speckly rock that makes up most of the photo. We have a metamorphic inclusion, and we have a dike here. And we also have a shoe. So your job here is to put the sequence of events in order from oldest to youngest. We've got the dike, the metamorphic rock, the granite, and the lovely shoe there. So put them in order from oldest to youngest. Go ahead and pause the video if you need to work on that or consult a friend. Okay, let's unravel this. Here's the crime scene. We need to do the detective work and figure out what happened, what geologic events, and in what order did those geologic events take place that led to this sort of situation. So let's just go. It can be overwhelming. The best thing to do is compare one thing to another and use those basic principles. The first thing that I notice is that the dike cuts through the metamorphic rock. Therefore, the dike is younger than the metamorphic rock. I can also see that the dike cuts through the granite. Therefore, the dike is younger than the granite. Thankfully, the dike doesn't cut the shoe, so I don't have to really deal with that too much right now. So I know the dike is younger than both the metamorphic rock and the granite. Now I just need to compare the metamorphic rock and the granite, and I think I've got it. Well, the metamorphic rock forms a clearly defined inclusion that is completely surrounded and encapsulated by the granite. Therefore, using the principle of inclusions, the metamorphic rock is older than the granite. So if I think I've got this, I would start with metamorphic rock existed first. Then the granite, the magma surrounded it, cooled into granite. That would be chapter number 2 in my story. Then the dike cuts through both of those rock types. And then someone steps on the ground and I take a picture at Joshua Tree National Park back in the day. So I would go metamorphic, granite, dike, shoe. And that would be option number D here on your list. So hopefully you're doing a little better here. If not, that's okay. You can practice. You can get on the internet and just type in relative dating exercises, and you'll probably get all sorts of fun examples. It's kind of fun. They're like little puzzles. These are what I like to call the geologic puzzles. Get it? And they should be in the newspaper right next to the crossword and the Sudoku if I was in charge. Okay, last one here. This is a photo. And let me see if I can walk you through it here. What you're looking for, oh, I actually made a mistake on this one. Let's ignore F in the hand there. Let's just do A, B, C, D. So which is the youngest feature? We have A, which is the gray rock here. B, which is this feature here. C is this light colored feature here. And then D is this feature that goes up and down through here. So which of those four, ignore the hand and the letter there, sorry about that little typo, is the youngest? Go ahead and pause the video if you need to. Okay, another great example of using cross-cutting relationships. This one's actually very similar to, going back a few, this one I gave you here, but this was just a diagram. I wanted to show you a real-world example of these sort of cross-cutting little dike features. So in this case, all three dikes, B, C, and D, cut A. Therefore, A would be the oldest. Okay, now we just look at how these dikes cut each other. It looks like D cut C, but then B, coming across here from upper left to lower right, cuts both C and D. Therefore, B would be the youngest of those four geologic features there. So hopefully you did pretty well with that one. Kind of fun, right? I enjoy these. These are fun to do in the classroom. We can roll through, a bunch of these and the students collaborate. So that it's a fun way to sort of test yourself. But look for features like this when you're on your next outing. Look for ways that you can use these relative dating features: original horizontality, superposition, cross-cutting relationships, and inclusions. Those are your guiding principles to carry you forth. And what we might do in the next episode is do a more complicated one with more features, something like you might see in the real world where it gets kind of messy, and see if we can work our way through it. But for now, we'll go ahead and close this episode 17, Relative Dating Principles. Hope you enjoyed it. If you want to support the channel, there are links under the video description. There's the thanks button, and we appreciate your time, and thanks for learning with me. Take care.